Okay, we're going to look at a combustion analysis problem, and the problem states that we have 2.78 milligrams of ethyl butyrate. Okay, and when we burn that, and its formula is like CXHY, that's a Y, gosh, OZ. When we burn that, meaning when it reacts with oxygen, it yields CO2 as a gas and water, liquid. Okay. We're also told that we produce 6.32 milligrams CO2 and 2.58 milligrams of water. Converting those milligrams to grams, okay, we would have 0.00278 grams of the ethyl butyrate. We would have 0.00632 grams of carbon dioxide, and we would have 0.00258 grams of water. Okay, we're asked to find the empirical formula of ethyl butyrate. Now, the problem is that this organic contains oxygen. The CO2 contains oxygen, the water contains oxygen, but those oxygens in my product could also come from the O2 that was in the air. There's really no way of telling where that O2 came from. So the only thing we're sure of is that the carbon and the carbon dioxide and the water, the hydrogen in the water, come from that organic compound. So the process is going to be to figure out the mass of the carbon in the products, the mass of the hydrogen in the products. Add those masses and subtract those masses from the mass of the ethyl butyrate. That will give us the mass of the oxygen that's in this ethyl butyrate. Once we have the masses of the carbon, hydrogen, and oxygen, we calculate the moles of each and then find the simplest whole number mole ratio, which will then give us the empirical formula. So stepping through that process, I would have my 0.00632 grams of CO2 times the molar mass is 44.01 grams in 1 mole of CO2. You can relate the moles of CO2 to moles of carbon, because for every 1 mole of CO2 I get 1 mole of carbon. I'm going to calculate how many moles of carbon that is, and then, because I have to apply the conservation of mass, I'm going to find the grams of carbon that is. So doing the math, I get 1.436 times 10 to the negative 4th moles, and I get 0.001725. That's a 5 grams of carbon. 0.001725. So now let's do the same thing for the water. Start off with 0.00258 grams of H2O. Convert that to the moles, 18.02 grams in 1 mole H2O times in 1 mole H2O, I get 2 moles of hydrogen. I'm going to calculate that number, and then to apply that conservation of mass, I'm going to find the grams of hydrogen. So the moles of hydrogen, when I do that math, is 2.863 times 10 to the negative fourth, and the grams of hydrogen is 0.002892 grams hydrogen. So I'm now going to calculate the mass of oxygen in CXHYOZ. To do that, it's the 0.00278 grams minus the 0.0011725 grams of carbon, and subtract the 0.123292 grams of hydrogen. I should get 0.002014. That doesn't look right. Oh, because it's not. I don't. No, don't. That's not right. It's this 0.000766 grams of oxygen. That looks better. So now using that number, 0.000766 grams of oxygen, convert that to the moles of oxygen, molar mass of oxygen, in 1 mole of oxygen. That gives me 4.786 times 10 to the negative fifth moles of oxygen. So now let's find the mole ratio. For the moles of carbon, I have 1.436 times 10 to the negative fourth moles of carbon. I have 2.863 times 10 to the negative fourth moles of hydrogen, and I have 4.786 times 10 to the negative fifth moles of oxygen. The smallest number is the 4.786 times 10 to the negative 5. I'm going to divide each of this to get the smallest whole number ratio. .786 times 10 to the negative fifth. That gives me 3 carbons, 6 hydrogens, and 1 oxygen. So the empirical formula is C3H6O. Okay. So there ends combustion analysis.